Hello, everybody, and welcome to the Decouple Podcast, where we explore the science and technologies that can decouple human well-being from its ecological impacts, and the politics that can make decoupling possible. Welcome back to Decouple. Today I'm joined by Zeke Hausfather, who's a climate scientist and energy systems analyst whose research focuses on observational temperature records, climate models, and mitigation technologies. Zeke spent 10 years working as a data scientist and entrepreneur in the clean tech sector, where he was the lead data scientist at Essus, the chief scientist at C3.ai, and the co-founder and chief scientist of Efficiency 2.0. He's also worked as a research scientist with Berkeley Earth, was the senior climate analyst at Project Drawdown, and the U.S. analyst for Carbon Brief. He holds a master's degree in environmental science from Yale and a PhD in climate science from the University of California, Berkeley. Zeke, that was a mouthful. You got a lot of qualifications, man. Welcome to the podcast.
Thank you. It's great to be on.
So Zeke, if you've heard other episodes, I like to ambush my guests with a little self-introduction. Give us the human side. We got those bona fides out of the way. I stumbled on them a little bit, but tell us a little bit about yourself and maybe what led you down your path towards becoming a climate scientist.
Sure. It was kind of an unusual path. I was always interested in environmental issues, and particularly as an undergrad, became really interested in climate. This was, shortly after the Kyoto Protocol had come out, and there was all the discussion around that. Was really into activism back in college, dropped banners off buildings, chained myself to people in corporate offices to get them to sign on to sustainability pledges, that sort of thing. And it was an interesting time because a lot of that actually worked. This was during the Bush administration when there wasn't much going on at the federal level, and environmental groups realized that pressure on companies could actually create, meaningful short-term change in a lot of cases.
Right.
But eventually burnt myself out on activism, went back to grad school, met a fellow in an energy modeling class while I was at Yale, who was about to graduate from Yale Law School, and had decided he didn't want to be a lawyer. But he had done his undergraduate at Harvard and been classmates with Mark Zuckerberg and a bunch of these other people, had gone on to start social media companies. And this was 2007. An Inconvenient Truth had just come out, and he had the brilliant idea to start his own social media company, but focused around climate and helping people reduce their climate impact. And he convinced me to join him, and we co-founded a company that was initially called Climate Culture, and it had a sort of virtual 3D island that represented different parts of your carbon footprint, and an avatar that could gain levels and unlock outfits as you commit to take actions to reduce your footprint. And you had a profile, could visit your friend's island, could play flash games to win carbon offsets from sponsors. It was very like 2007 gamification.
Yeah.
And this was an Inconvenient Truth had just come out, so everyone was focused on climate. And then the financial crisis hit. And we realized we needed to actually figure out a way to make money. And while we got like 50 or 60,000 people using this niche social network, that wasn't really a viable long-term option. And so we pivoted, turned it into a company called Efficiency 2.0, realized that all of these algorithms I had designed around carbon footprint calculation could be used to estimate home energy use characteristics, and sort of competed against O-Power in the behavior-based efficiency space for a while. And so I ended up doing that and similar things further for about a decade. But during that time, I got more and more interested in sort of climate science. When I was living in Amsterdam, before grad school, I started reading this blog called Real Climate. It was put out by a bunch of, at the time, young, early career climate scientists like Gavin Schmidt or Michael Mann, Stefan Ramsdorf, who are sort of some of the more senior people in the field these days, and got into this whole weird world of climate science blogging, which sort of hit its peak, around the late 2000s. And a really pivotal moment for me actually was when I got into an argument with a major climate skeptic, this guy named Anthony Watts, who runs, I think, what is still probably the most trafficked climate skeptic blog. I'm not sure how many people still read blogs. And it was around a somewhat esoteric issue on surface temperatures. Essentially, the number of stations available at the time to researchers dropped precipitously from like 7,000 stations worldwide to 1,200 in 1992, in part because the World Meteorological Organization had done a big effort to collect all this old station data before 1992, and after that set up a network of 1,200 stations that automatically reported every month. And no one had really gone and collected all the other data that had come out since then that was, sitting in paper logbooks everywhere. And so his whole thing was like, look, they're throwing out all the stations that are cooling and only keeping the ones that are warming. And I'm like, that's quite a claim. And, there's an easy way to prove that. Just look to see if there's any difference in the rate of warming between the stations that stop in 1992 and those that don't.
Yeah.
And he was like, well, if that's so easy, why don't you do it yourself? And I realized that, hey, all this sort of data science work I'm doing for my day job in the private sector, I could easily look at a simple climate problem like that. And so I wrote some quick code to, download all the global temperature data, to calculate, the trends at each station, and then also as part of that to put them on a grid and calculate the global temperature. And it turned out I got a result that was pretty much the same as what NASA, NOAA, and all these other groups get. I was like, okay, that's pretty cool. And I was like, okay, what other interesting issues can I then use this bit of code I wrote to look at? And one of the big issues that was being debated at the time was something called the urban heat island effect.
Right.
And
that's
essentially
just
the idea there is
mass issue from living in a concrete jungle.
Most of our weather stations are located where people live, right? There's not too many.
Okay.
These days they're more automated stations, but particularly back then, there weren't too many. There were way out in the boonies where people trekked out every day to take measurements, right?
Right.
And so there's a concern that since we know that the urban heat island is real, the concrete jungle warms up the environment, and most of our stations are near where people live, at least over land. So obviously 2/3 of the Earth is ocean, and we have plenty of measurements there. There was a real concern that we might be sort of overestimating the rate of warming by sort of conflating urbanization and its impact on the local environment with global warming. And so I did a quick analysis on that using some of the code I'd written, posted on a blog. Some scientists at NOAA came across it and reached out to me saying, hey, this is really interesting work. Would you be interested in co-authoring an academic paper on this subject? And I was like, okay, that sounds like fun. Finally came out in 2013 in the Journal of Atmospheric Research, JGR, Journal of Geophysical Research, Atmospheres, and got a decent amount of attention. And I had a lot of fun with the whole process. And I was like, okay, this was a lot more fun than my day job.
Right.
Is there a way I can eventually make this into my day job? And so, ended up writing a bunch more papers, going to a bunch more conferences, doing a lot of sort of science communication stuff on the side as well, which sort of the blogging was a big part of, and eventually going back and getting my PhD as a way to, make my passion into my career.
Right. That's a really interesting blend of your work, I guess, working for yourself, private sector work, should we call it, academia, your own interests. You've kind of melded that all together. It's not what I was expecting. Maybe I thought maybe you're more of a stodgy academic who'd now gone into policy work, but it sounds like you've had a pretty varied life so far.
I've never had a traditional academic career per se.
Yeah.
But it was interesting going into the PhD program, having published 10 papers, but none in a traditional academic format.
Right.
A very different experience than most people, but
right. So now you're at the breakthrough, and maybe we'll get into that a bit later, but I wanted to, for the listeners' sake, dive a little bit into what I wanted to cover with you today. And I mean, the podcast, the motivation for doing the Decouple podcast, I think for getting attracted to elements of eco-modernism was coming for me out of a climate concern. And I'd read a number of books, 6 Degrees by Mark Lynas, The Sixth Extinction by Elizabeth Kolbert, The Uninhabitable Earth, a number of books that had got me pretty riled up about it. As I've been doing the podcast, I've been focusing a lot on nuclear energy, but a number of other topics, political topics, philosophical topics related to environmentalism, but I really haven't touched much on the science of climate change beyond an early interview with Mark Lynas. And I mean, his book, I think, is really excellent. It's drawing on IPCC reports to paint a picture of what the world will look at each sort of degree. But he talks a bit less, I think, about, probabilities that we're going to arrive at certain thresholds, at certain degrees of warming. And I think what I've been noticing, I've had a few guests on, and I've sort of been trying to think about the sort of climate concern spectrum and where people fall upon it. And certainly, I think it's easy to define sort of the outliers on either side, the sort of the catastrophism of Extinction Rebellion, Derek Jensen, Greta Thunberg, for instance, and the kind of old school denialism, maybe of George Bush era. Maybe that's like Tucker Carlson. I'm not actually sure exactly where he stands, but this kind of middle section's a bit more tricky. Certainly, I think a lot of folks that maybe used to be on that sort of denial side of things are now in the, well, climate change is real, but it's not that big of an issue, especially if we choose the right discount rate. Folks like Bjorn Lomborg.
Yeah, we have a term for them. We call them lukewarmists.
Lukewarmist. There we go. Yeah. So I'm trying to like flesh out this language and sort of decide where I situate myself. Because certainly I started off in a very catastrophist camp. I think I'm still quite alarmed. I know alarm, all these terms are kind of pejorative. But yeah, I mean, tell me about where you sort of situate yourself on this spectrum, if you're comfortable doing that. I've had a bunch of guests who just said no, they wouldn't, and others where I was like, use a pejorative term for yourself, and they said no, and then I've given people like a scale of 1 to 10 to use. I'm not sure if it's useful language at all, but I mean, yeah, what are your thoughts about?
Yeah. So it's hard to define because you're conflating a bunch of different issues, right? On one side, there's the question of how bad could climate be, and the other side, there's the question of how bad will climate be.
Yeah.
The former, in some ways, is it depends on less uncertainties than the latter, because the latter, really depends on what we do about it.
Right.
But on the side of how bad could climate be, I mean, it could be really, really bad, right? If we burned all of the coal deposits on the Earth, we would have pretty massive amounts of warming. And the more we learn about our planet, the more caution we want to have around, pushing it too far out of the range that's characterized the last few million years. There certainly have been a lot of large climatic changes that have occurred in the Earth's more distant past that we don't always have great explanations for. And a lot of work that has been done around, potential longer term shifts, particularly under very high concentrations of CO2. There's a paper by Tapio Schneider and his group at Caltech, I think 2 years ago now, where they looked at very high resolution cloud resolving models, and they found that about 1,300 or so parts per million, at least in their models, you suddenly had most of the stratocumulus cloud decks covering the Earth's oceans evaporate, and you had about 6 degrees additional warming in the course of a few decades on top of what was already 4 or 5 degrees warming. Obviously that's one model, and it's a limited sort of column model, and we don't know for sure any of these things, but I think the Earth's past and the magnitude of shifts we've seen there should make us very cautious. And we also, I feel like we tend to get a little complacent when we talk about degrees of global warming, right? The last ice age was about 5 degrees colder centigrade than today.
Right.
We're talking in a world where we really tried to emit all the fossil fuels we could. It's not out of the question we could get 5 degrees centigrade warming, if not this century, certainly next century. And so, if we wanted to make things bad, we could make things bad. And while I'm hopeful that a more prosperous future will, make humanity a lot more adaptable to those sort of changes,
right.
I'm also a little skeptical at how equitable that future is going to be, given, current political and social trends. And also, humans aren't the only thing that matters, right? We can adapt easily. The natural world can adapt a lot less easily. There's a lot of species that are climate constrained in terms of where they can live. And while humans can help species adapt a little bit, we can genetically engineer plants to be more heat tolerant. We can, relocate species by hand to get them into new climatic ranges that fit them. There's limits to that, right? And so I'm worried about sort of a prosperous human future in a graveyard of nature. And
Right.
that's not a world I want to end up in either. And so, I'm alarmed in a sense around the potential impacts of climate change, but I'm also cautiously optimistic in our ability to deal with the problem. One of the things I've published a lot on is future emission scenarios and sort of where the world is heading.
Right.
And a decade ago, it seemed like a world of 4 degrees by 2100 was a real worry, right? China was building a coal plant every 3 days. Global coal use had doubled in a decade. And the idea that the 21st century would be the century of coal was not a crazy idea. Obviously there are people who push back on that, are like, look, there's a lot of other technologies that are out there. There's no reason to think that we're going to be burning this dirty rock that's causing all these air pollution problems for the next century. But at the same time, energy transitions historically have happened very, very slowly. If you look at Apocalypse Neil and some of his work, for example. And so, we certainly couldn't rule out those sort of scenarios. 10 years later, we're in a very different world. Global coal use peaked back in 2013. It's now in structural decline, according to the latest IEA report. The price of solar and batteries has fallen tenfold in a decade. The price of wind has fallen threefold. There's a lot of neat work being done on small and modular reactors that we'll see if they end up being cost competitive. But regardless, the global energy future is very different now than it was a decade ago. And now it seems like global emissions may have already peaked, and if they haven't already peaked, they're certainly entering a long plateau instead of continuing to increase. And so a world of plateauing emissions, which seems to be the sort of current policy pathway we're on right now, is a world of about 3 degrees warming by the end of the century. And obviously, continued warming after that, as long as emissions remain above net zero.
So that
in a world of
the end of the century thing has always struck me as interesting. And I know there's some extended pathways that the IPCC has put together for a variety of their RCP scenarios, but with things just kind of abruptly dropping off at 2100. I mean, my son will be 82, God willing, in 2100. But I mean, certainly trying to think in the long now terms of someone like Stuart Brandt. How do things look in 2200, 2300? How well is that understood? If we manage to get to say even net zero emissions, which I think is fanciful perhaps, is the climate anticipated to stabilize at that point? Or will there be a radiative forcing that will kind of continue this temperature rise, beyond that 3 degrees at 2100, let's say? Because for me, I think that's part of the concern that drives me more on that spectrum towards alarm or catastrophism is like, okay, well, yeah, I care about my kids, grandkids.
Yeah. Posterity is a powerful force.
Yes.
And, I sympathize with you, right? Or empathize, I should say. I have a 2-year-old or 3-year-old now.
Nice, yeah.
And so she is very much going to be alive in 2100. And so even though, the world doesn't end in 2100, even though a lot of our models do.
Right.
And so we need to start looking at these longer periods. That said, once you get that far, it's really hard to conceptualize, what energy will look like, what humanity will look like. Imagine someone 100 years ago trying to think of what the, today would be. It's a very different world. So it's tough to look that far out, but I think it's useful. As to your question about warming, effectively, warming stops once we get to net zero with some uncertainty. There's been a lot of modeling around this, particularly in the last year or two, that finds that once you get CO2 emissions to zero, holding everything else constant, you end up with sort of plus or minus half a degree warming over the century after that. And the reason for that is you're essentially having two countervailing factors at play. On one hand, once you get emissions all the way to zero, the carbon sinks, the atmosphere and the ocean keep sucking up some of our historical emissions.
Right.
And so atmospheric CO2 starts falling quickly at first, and then eventually tailing off as the sinks in the atmosphere reach a new higher equilibrium, and you end up having to have like very, very long-term processes to get rid of all the extra carbon we've added. And at the same time, the oceans are out of equilibrium today. About 90% of the heat that's being trapped by greenhouse gases is being absorbed by the oceans, and they're heating up much more slowly in the atmosphere because of high thermal mass of water. And so that continues to happen over hundreds of years, quickly at first, and then more slowly as sort of the surface layer warms up to match the atmosphere, and the rest of the deep ocean is a very, very slow warming process.
Right.
And it turns out that those two curves, rapid ocean surface warming tailing off and rapid falling of CO2 tailing off, effectively cancel each other. So the additional warming you get from the oceans continuing to heat up is canceled out by the cooling you get from CO2 falling in the atmosphere. And so you end up with flat temperatures once CO2 reaches zero. Now, the real world is a little bit more complicated than that for two reasons. One is CO2 is not the only greenhouse gas. You also have all of these, you have methane, which is a strong greenhouse gas responsible for about a quarter of the warming we've experienced today, but has a very short atmospheric lifetime. So if you were to cut all greenhouse gases to zero, global temperatures would actually fall pretty quickly by maybe, half a degree, or at least a third to a half a degree, as all of the methane drops out of the atmosphere in the next 2 decades or so. But there's another short-term climate forcing, or factor, I should say, that has the opposite effect, which is sulfate aerosols.
Yes, So the air pollution improves and we heat up, right? Because is that a
exactly effect? So all these sulfate aerosols reflect incoming sunlight, contribute to what people call global dimming, which is a strong cooling influence. But it also
solar
turns
geoengineering,
out,
right?
Yeah, we are solar geoengineering by burning coal, and And so as all of that falls out, you end up having a bunch of short-term warming. And it also turns out conveniently that our best estimate of the additional warming you'd get from getting rid of these cooling aerosols is roughly the same as the additional cooling you get from cutting all the methane in the atmosphere that humans have added. And so those two kind of cancel each other out too. So essentially, if you get zero CO2 holding everything else constant, you have pretty much flat warming going forward. And if you get zero all of greenhouse gases and aerosols, you have roughly flat, maybe slightly cooling by a tenth or two of a degree, because there's big uncertainty in the actual forcing of aerosols going forward. But that's, I think that's good news fundamentally, because it means that we have a lot more agency of controlling the future climate of our planet than if we lived in a world where there was like half a degree warming in the pipeline that we were going to experience no matter what we did.
And in terms of the the positive feedback mechanisms that start to click in with potential methane clathrate releases from permafrost and the Arctic seabed.
So that's the second caveat.
There we go. Yeah, hit me with that. Give me some bad news.
So the good news is you don't have to worry much about clathrates, in part because most undersea clathrate formations or hydrate formations are relatively stable. And even if they are destabilized, the evidence we have is that most of the methane released is absorbed by the ocean on the way up to the atmosphere. So there's not actually much outgassing from the top of the ocean. Maybe if we had some very, very extreme warming events, you could have large scale methane clathrate releases. But
what are the other positive feedback loops to be concerned about?
So one of the big ones is methane permafrost, and there it's a bit complicated, right? Because it's mostly like the methane doesn't all melt at once. It's a very slow process, sort of from the top down. Some areas faster than others, like south-facing slopes faster than north-facing slopes, even in the same area. Right. And so what you end up having is not so much a concern about methane from permafrost, because it happens so gradually that most of the methane decomposes into CO2 over the time scales at which the feedback has a big effect. It's more the carbon that ultimately comes out of the permafrost that matters for the climate. And there, some of it is counterbalanced by more vegetation growing in permafrost regions as it warms, but certainly by no means all of it. And a lot of the amount of permafrost that melts is proportionate to the amount of warming. Permafrost isn't so much a tipping point. It's not like you suddenly pass a point and all the permafrost disappears, or even will eventually disappear. It's scales with the amount of warming you have. Like at 2 degrees, you get this much, 3 degrees, you get this, degrees, you get this much. But exponentially, the more warming you get, the more permafrost melt you're going to have in the long run, and the more permafrost carbon you're going to have in the atmosphere. And so what that means is if we can stabilize warming at 2 degrees above pre-industrial, we're not really going to have that much committed long-term permafrost carbon release. If we're at 3 degrees, it's going to be a moderate amount, maybe by 2100 equivalent to 3 or 4 years of human emissions. But if we start getting much above that, 4 degrees, 5 degrees, then we're committed to a lot of long-term permafrost melt.
And the methane has as you were saying, a short-term effect that's what is that? I've heard estimates like 24 to kind of 80 times more potent than CO2 in the atmosphere.
It depends on the time frame. While it's actually in the atmosphere, it's like 120-ish times more potent. But again, it starts leaving the atmosphere almost immediately, portions of it, and almost all of the methane is gone in about 12 years after it's been released.
Let's step back a little bit. I meant to sort of define some terms recently. I found reading Bill Gates' book, How to Avert a Climate Catastrophe, was useful from the sense of getting a perspective of just some basic numeracy around how much humans are emitting. So from what I understand, since the Industrial Revolution, we've done a little over 1 trillion tons. And we do about 50 gigatons a year of CO2 equivalent. So like I think 35 of CO2, and then the rest is methane and other gases that have
35 of CO2 from fossil fuels, about 5 of CO2 from land use changes.
Okay. And then some other 10, methane. So 12, 50 gigatons a year. I mean, but what's fascinating about that is that in 20 years, we will release the same amount of CO2 as we've historically released from the Industrial Revolution up until now. Like those are the kind of numbers that have me kind of freaking out a little bit, especially, I was talking with Mark Lynas and we were talking about the end Permian extinction event, and I guess the basalt lava tubes that released lots of CO2 in the air over maybe tens of thousands of years, and the climate impacts that had. Is there any, and it's very difficult obviously to compare these geologic eras that are so separated, land masses are different, continental tectonics have moved, but What do you think about that line of reasoning that these changes are so abrupt compared to the climate record and the degree of temperature swings that we're seeing in the geologic eras prior?
Yeah, I mean, we don't have great high resolution data from the distant past, so it's hard to know precisely how much change we had in a century timescale.
Right.
But from everything we can tell, the Earth is warming much faster now than it has in almost any period in its past history.
Right.
Simply because most of the large scale warming events that previously happened over the course of tens, if not hundreds of thousands of years. And we've seen, 1.3 degrees C warming already just over a century. And so that's a concern for a number of reasons. One, as we talked about earlier, there's a real concerns around adaptive capacity in the natural world to that rate of change. Nature can adapt to big swings over long periods of time if it has time, right? Corals are incredibly sensitive to temperature, but there were corals alive in the Eocene. They were just adapted to a much warmer climate than the one we have today. But it also, creates challenges for human systems too. We can adapt much more easily to a longer time scale. Whether or not there's sort of big unforeseen feedbacks that will lead to much more warming than, what we predict will happen, I'm a little more skeptical on that front. Modern Earth system models have a lot of these processes in them already. And while there certainly is a risk of unknown unknowns, the further we sort of push climate away from the Holocene, period where it's been, I'm hopeful that we'll avoid the levels of warming that would make those sort of things more concerning. For me, essentially, if we can keep warming below 3 degrees and hopefully below 2.5 degrees, I think we're minimizing the odds of a lot of the potential big sort of tipping point processes that could really enhance global temperatures dramatically in a short period of time. That said, there are plenty of other tipping points and tipping elements that are concerning at lower levels of warming. Certainly all the coral reefs disappear once you get much above 1.5 degrees global warming. Though some areas will be more sensitive than others. You're committing the world to a lot of long-term sea level rise at 2 degrees warming over the next few centuries, simply because, as long as temperatures stay high, the sea or land ice gradually melts, you have more ice sheet movement, you have more sea level rise, but that doesn't necessarily increase global temperatures, right? And for things like permafrost, they're not so much tipping points as feedbacks. The warmer it gets, the more permafrost melt you get. And so by limiting warming, you sort of limit the amount of melt you're going to get. And so, for me, the tipping points are worrying on an ecosystem level or like a regional climate level. But in terms of global climate, I think if we can limit warming to, below 3 degrees and certainly below 2.5 degrees, I'm not too worried about those. But that said,
I think something
the small risk of catastrophe is always something you should keep in mind when hedging your bets. And, we also have the ability to, overshoot and recover, right? With negative emissions technologies or solar geoengineering or something else. Like if we get to the point where we're like, oh shit, there was this really bad thing that now we all see coming that no one really saw at 2.5 degrees warming, we have some, emergency arrows in our quiver to deal with that. We could temporarily geoengineer until we can suck enough carbon out of the atmosphere to get down to below 2 degrees or whatever threshold we discover is associated with this unknown tipping point. I hope we'll never be in that situation because the politics and geopolitics of that are messy. But
and that's something that I find very interesting because I find a lot of the lukewarmists, they'll seize on a couple of elements, right? They might just talk in isolation about the challenge of sea level rise or of the Hadley zones increasing and maybe more drought stress on certain bread baskets. But they'll say, okay, but there'll be more tractors, there'll be more this, that. But when I just think it's very hard to fit in all of the variables, right? From like water shortages due to glaciers depleting and these big areas of the world with maybe the majority of the world's population dependent on glacial flows, ocean acidification, those droughts and food stresses, refugee flows, increasing in kind of avocado politics, as we've talked to Nils Gilman about on the podcast. Hurricane Maria apparently set Puerto Rico back by about 20 years in terms of its physical infrastructure. And this idea that we're going to be able to, through and further development, adapt well to climate change, I find slightly challenging from that perspective of kind of towing along this anchor behind us of all of the various climate impacts, be it extreme weather events or these other shortages. And I'm reminded of I've talked about this a number of times, but James Lovelock, one of my favorite humans, has spoken about how, yes, human beings are very capable of innovation and using technology to match challenges. But when we end up becoming dependent on them because we've destroyed an ecosystem life support service, it's kind of analogous to living on dialysis. You have to constantly maintain this machine. And that has some kind of a net drag on human capacity and societal capacity to continue adapting. So maybe I have a bit more of a pessimistic outlook than you in terms of, we'll be able to geoengineer and then develop carbon sequestering technology that can draw down. And I do want to get to that as well with you, that specific topic of a lot of these models from the IPCC depend upon getting to actual negative emissions. But just on that topic of
my point wasn't so much that we should plan on geoengineering. I don't think we should. My point was if there is an unknown
right
in these more modest warming scenarios, it's a useful thing to have.
What do you think, though, within the climate discourse in terms of, like, again, as I was mentioning, that laundry list of variables of which I probably only touched upon like 20 or 30% of the big impacts and stresses that climate change can pose to humanity, like that, versus, again, the lukewarmist being like, this one or two problems, not a big deal, but how those all interact with each other. That's not like,
I think it's a really important point and a really tricky one. And a lot of, what you suggest the lukewarmers are doing is also a big flaw of climate economics. Like any of these studies are like, the economic damage of climate change will be equal to 4% of GDP under 4 degrees warming. It's like necessarily very narrow in terms of the type of impacts it can quantify. Like a lot of the early economic assessments of climate change were almost entirely about like agriculture impacts. A lot of them didn't even have sea level rise impacts. They've gotten a little better at that, but it's a real challenge. But I think, from my perspective, the impacts are large enough, particularly to the natural world, but also to the human world, that it, well justifies aiming to limit warming below 2 degrees. And I think, we've made a lot of technological progress that puts that on the table in a way it wasn't 5 or 6 years ago. But what worries me personally is the remaining uncertainties, not in terms of long-term tipping points, but just in terms of how much warming we'll end up with in the near term, just based on what we know. And, by that, I mean, really, two big uncertainties on top of our own emissions, which we have control over. The first of which is what we call climate sensitivity. So essentially how sensitive the climate is to our emissions of greenhouse gases. And that involves the interplay of a lot of different things like water vapor feedbacks and albedo feedbacks and aerosol forcings and all these other things. But essentially, if we double the amount of CO2 in the atmosphere, our best estimate now is that we'll end up with somewhere between, about 2.1 and maybe 4.3 degrees warming. And that's a pretty big range, right? 2.1 would not be that bad if we double CO2, and hopefully we won't double CO2. 4.3 would be really bad. The good news is that range is a lot narrower than it used to be. I was an author in this big review this past summer that specifically narrowed that range and sort of helped chop off some of these very long tails of the distribution. Like previously, we couldn't say we could rule out like 5.5 or 6 degrees warming for doubling CO2. And now we're, we can never fully rule out anything, but we're a lot more confident that those are unlikely based on sort of the combination of multiple lines of evidence. But the other big uncertainty that gets a lot less press that's equally important is what we call carbon cycle feedbacks. And permafrost plays into that as part of the equation there, but there's also a lot of other carbon cycle feedbacks. So as the world warms, the ability of the land and the ocean to take up our extra emissions, because they're taking up, about 60% of what we emit right now does not end up in the atmosphere. It ends up in these carbon sinks in the land and the ocean. But we know that those sinks are going to weaken as the world warms. And exactly how much is a big question mark. And so you can end up with, another couple hundred at the extreme parts per million CO2 if the carbon cycle feedbacks are on the high end of sort of the range within the models. Or you could have less CO2 if they end up in the low end than we currently predict. And that's a big uncertainty that we need to resolve as well. And so the challenge is if you combine those uncertainties, while we can say that, a current policy world is probably going to end up with 3 degrees warming, we can't rule out 4 degrees or even, at the extremes, 4.5 degrees warming under a current policy world. And that's what worries me, right?
and to what degree are the models
big uncertainty?
Yeah, to what degrees are the models improving with more data and more computing power? Like, is there a quantum leap in like you mentioned that you'd been part of this paper where you're narrowing down the potential temperature rises at a certain level or parts per million in the atmosphere. Are things improving? Is there a general sense of that in the climate?
So certainly we're making a lot of progress on understanding these uncertainties. The big models, the like supercomputer models that everyone focuses on, don't always help on all those issues. In fact, they've kind of made things a little worse on the climate sensitivity side. Because the latest generation of models, the ones that are being featured in the upcoming IPCC 6th assessment report, most of them are pretty in line with what the previous generation of models estimated. But there's this subset, about 15% of them, that are really, really sensitive to CO2, have like 5 degrees plus warming if we double CO2, right. Which most people who actually work in the climate sense world don't think is very plausible. And certainly most of the models that show that much or that high sensitivity are not very well in line with historical observations. In terms, they predict more warming than the world has actually experienced to date, for example.
So historically, like up until now, more has been predicted than has actually occurred. Is that correct?
In the subset of models that have very high sensitivity.
Oh, gotcha.
Overall, if you look at the average of all the models, what they predict is pretty much
what's happened,
spot on with what's happened. But the ones that are really, really sensitive, that say that like if we double CO2, we'll get 5 degrees warming, they tend to show too much historical warming, particularly in the last 30 years or so.
Okay.
Because a lot of them have this weird thing where they have to match the high sensitivity, they also have high aerosol forcings. And so what that ends up with is a 20th century that has almost no warming, followed by this huge spike in warming in the last 30 years as global aerosol emissions start to decline and CO2 emissions skyrocket. In the real world, we haven't seen that, right? Certainly we've seen, rapid warming since the 1970s, but it's been pretty linear. It's not like suddenly shoots up in the last 2 decades. Anyway, right. So there's reason to think that some of the very high sensitivity models in the latest generation of models are not reliable in that sense. In other metrics, in terms of matching historical rainfall patterns or whatever, they might be well improved over the previous generation. But for climate sensitivity, they're somewhat problematic.
So we've been talking a little bit about how like emissions may be plateauing now. I know Ted Nordhaus and Ken Caldera have a long bet on that. But what does that mean in terms of ongoing parts per million increases in the atmosphere if our emissions plateau? I mean, that's obviously a good start, but the challenge is to get down towards zero. What does a plateauing of emissions look like in terms of where we're at? We started at 280 pre-industrial, we're 417, 418 today.
Yeah, maybe? So a world of flat emissions is a world where we continue to add about 2 to 2.5 parts per million of CO2 per year to the atmosphere.
Okay. Gotcha.
And so that means we end up with close to 520 or 530, maybe 550 by 2100 in a world of plateaued emissions. Now, okay. I don't think it's very likely that we'll just have flat emissions for the rest of the century. I think it'll plateau, in a more pessimistic world where you don't get our act together on climate change. I still think it'll plateau for maybe 3 decades and then start declining, just because I don't really see fossil fuels getting cheaper, and I see clean energy getting a lot cheaper just due to market forces and innovation, and the fact that so many people care about this issue, even if there's not strong government policy, and are putting a lot of money behind it. But that said, a sort of world where we did have flat emissions for the rest of the century, we'd continue to add that much, 2-ish parts per million CO2 to the atmosphere every year, and we'd continue to have warming of about 0.2 C per decade.
So let's talk a little bit about how many of the IPCC models call for actually getting to a negative emission scenario. How do they forecast that? Is that just taking advantage of natural sinks, or is that with bioenergy, carbon capture and storage, or even like engineered mechanical carbon capture and sequestration? I mean, I had a show recently on mechanical carbon capture and sequestration, and it's very interesting, but when you start looking at the amount of infrastructure required and the energy required, and the fact that it doesn't, contrary to the use of fossil fuels, which brought a lot of wealth to us, I mean, it's a drag on us again to develop all the infrastructure to pull this stuff out of the atmosphere. It's the right thing to do for the climate, but it doesn't make people rich or societies more wealthy. What's your take on that? Is that sort of pie in the sky, the dependence of these models on negative emissions, or do you have a more optimistic view of that?
So when we talk about IPCC models, we really need to differentiate between 2 different types of models. On one hand is the climate models, which most folks are more familiar with.
Right.
Those just take emissions, or actually specifically, usually they take concentrations in the atmosphere as an input, and then figure out what happens to climate based on that.
Those are the
On the other
those
side,
are RCPs, right? The relative concentration pathways, or
the RCPs are the things that are used by climate models to run the climate models. The climate models themselves are like CMIP models, CMIP3, CMIP5, the new CMIP6.
Gotcha.
But what creates those RCPs, or the new SSPs, which are being used for the latest generation of models for the upcoming IPCC report, are a thing called integrated assessment models, or IAMs, which itself is a confusing term because it's used to describe two very different types of models. On one hand, like Bill Nordhaus's DICE model, which is a very famous climate economics model, is called an integrated assessment model, but that's not the type of thing that's used by the IPCC to create its emission scenarios. Rather, they're really better called energy system models. They're essentially global energy optimization models with their own assumptions around future technology prices and policy strengths and whatnot. And the way they're usually run is they sort of run a baseline version of the model, which sort of says what happens if the world stays the way it is today in terms of policies, or the way it was 10 years ago in some cases. And then various mitigation scenarios that say, okay, if the world wants to limit warming to 2 degrees, this is the optimal mix of energy in different regions to get us there, right? And so those models, particularly for very ambitious mitigation scenarios like 2 degrees or 1.5 degrees, tend to be very bullish on negative emissions. And the reason for that is because they assume that it's very expensive to cut emissions in the near term, and they assume that these sort of negative emission technologies will get a lot cheaper by the end of the century. And so therefore the optimal solution in this sort of model is to overshoot, maybe get to 1.8 degrees in the middle of the century, and then suck an enormous amount of carbon out of the atmosphere to get down to 1.5 by the end in some of the 1.5 scenarios, for example. And the technology that those models mostly rely on for that is something called BECCS, or bioenergy with carbon capture and storage. And the idea behind BECCS is essentially you grow an energy crop, some energy dense fruit or switchgrass or whatever, and you convert that into electricity by burning it. And then you capture the carbon that comes out of that process and you bury it underground. So you get carbon negative electricity, which the models love because they're like, sweet, two birds with one stone. In the real world, bioenergy is a lot more challenging. And the scale of bioenergy employed by these models, BECCS specifically, is staggering, right? Some of these models have 2 to 3 times the land area of India devoted to BECCS by the end of the century globally.
Jesus.
So you're really talking about like planetary scale engineering here.
Right.
And so there's a couple problems with this approach. One is that it reflects the technological conservatism of a lot of these models. The models that are used by the IPCC tend to lag well behind what's happened in the real world, in part because the IPCC process is structured such that they need those model runs to be done many years in advance of the IPCC report, because it takes years for the supercomputer climate models to be run.
Right.
And so a lot of the current models that are being used in the upcoming IPCC report have technology cost assumptions from like 2012 or 2013, right? As an example, in all of the models used by the upcoming IPCC report, they assume that solar prices in 2050 will be higher than they are today.
Okay.
We've already seen large enough declines in solar prices that it's past what the models assumed would happen in the year 2050. And so if you look at models that are more up to date, like the IEA World Energy Outlook, which is updated annually, or some of the models by folks like Shell or BP or whatever, they tend to be much more bullish on renewables than the IPCC, the models used by the IPCC. And therefore, they also tend to be much more bullish on near-term emission reductions being cost effective. And so you don't need as much negative emissions in the more up-to-date models than you do in the models used by the IPCC. So that's, one big problem they have. And the other is in general, there's this assumption around low cost negative emission technologies with not too many limitations in the distant future. And if that happens, it would be great. I would jump, out and run down the streets waving my arms saying, we've created cheap negative emissions. We can solve climate change with no problem at all. But betting on that is problematic, and it ends up being a hell of a moral hazard, right? You're essentially following a pathway that's purposefully overshooting in hopes of some, miracle technology swooping in and saving everyone at an unimaginable scale later in the century. And so, I think that there has rightly been a lot of criticism of those models, and that the assumptions around very large scale negative emissions should be taken with a lot of skepticism. At the same time, I'm a little worried there's been a tendency to sort of throw the baby out with the bathwater around negative emissions. Even if they're not going to be counteracting half of all of our current emissions today by the end of the century, they're still going to be playing an important role. And part of the reason is that there is this sort of long tail of hard to decarbonize parts of the economy, things like industrial heat, shipping, aviation, agriculture, where we don't really have great solutions today, and we're probably not going to for at least the next few decades. And so, there is certainly a world where negative emissions aren't being used at a huge scale, but they are being used at a reasonably large scale to sort of counteract the sectors that we can't effectively decarbonize yet or fully decarbonize yet.
Oh, it's wild thinking about two land surface areas the size of India being devoted to bioenergy crops. I mean, I think the history.
One of the models says 5x, I think.
That's wild. And I know I was interviewing your colleague Sieber Wang on the Tsinghua climate models that China, or that this prominent Chinese think tank has put forward, with their goals of hitting net zero by 2016. I think they were heavily reliant on BECCS as well. So yeah, I mean,
BECCS has the weird distinction of being one of the few technologies that was first invented in a model.
Wow. I mean, there's this joke about like cutting down trees and dumping them in mine shafts as a way to to sequester carbon, but I guess making electricity out of them is useful. But it's interesting, like looking at the some of the early utility models for carbon capture at coal plants, for instance, and you need to burn about 20 to 30% more coal to run the scrubbers to sequester the carbon, which right now is being used to actually just pump more oil out of an adjacent oil field.
Yeah.
So it's,
coal with CCS is also the other thing the integrated assessment models used by the IPCC love are fossil fuels with CCS, particularly coal with CCS, which again, I think is a bit of a relic of them being using prices and technology assumptions that are almost a decade out of date now, right? Coal with CCS is a really hard sell in a world where the economics of coal are already pretty dismal, right? It's not like adding a CCS unit on top of coal makes the economics better. And so, I'm pretty bearish myself on coal with CCS outside of maybe some industrial settings. I think gas with CCS has a much larger potential as a technology, which is also something the latest IEA, the big report the IEA put out last week agrees on. They're also much more bullish on gas with CCS, in part because it can help fill the gaps between renewables better, but also because it can help with industrial heat decarbonization a lot more effectively than coal can.
So what's your take on the shale revolution in the States in particular? It seems to have really given a second breath to the fossil fuel era. We were talking about peak oil not so long ago, and fracking has certainly opened up a new kind of fossil renaissance. But emissions in the States have declined quite rapidly as a result of the switch from coal to natural gas, with the proviso of a methane leak rate below 3%, which I think is being achieved. But I know there's controversy around that. I talked to Ted about this a while ago. He was
so when you're talking about methane leak rates, it gets complicated, right? 3% is the cutoff for an equivalence over a short period, like 20 years. If you look at the full century, you'd need like 10% or so leakage to have equivalence.
Wow. Okay.
9%, I think. It depends a bit on what you're assuming for the efficiencies, because new gas plants are a lot more efficient than existing coal plants or even new coal plants.
Right.
Anyway, comparing methane and CO2 is complicated. I have a good paper on that I wrote a couple of years back with Ken Caldera and some other folks that I'm happy to share.
Right.
But yeah, so the methane revolution, or the shale revolution, I should say, is complicated from a climate standpoint. It's undeniable that shale gas has played a huge role in killing coal. And in fact, is the single biggest driver of declines in US CO2 emissions, more than wind, solar, or anything else to date. At the same time, it's led to a resurgence in US oil production. It's driven down the cost of oil globally, which leads people to make consumer decisions that are around like buying big cars and things like that are not ideal for the climate. And it's also led to a lot of methane releases. Our best estimate is that the leak rate of the whole natural gas system is somewhere around 2%, but that's still a lot of methane going into the atmosphere. And a lot of flaring of natural gas and releasing CO2 through that. So I think on balance, it's probably been a good thing, but it's a good thing that needs to wind down quickly. I think shale oil is going to be a tough sell in a world of high electric vehicle uptake, just because it's one of the more expensive ways to produce oil compared to like Saudi Arabia or somewhere.
Mm-hmm.
And then shale gas isn't going anywhere soon, but we're going to have to see a world of declining gas use, but continued gas use for a while. So one interesting thing is, if you look at, there's been a whole host of models published recently looking at how you could decarbonize the US by 2050. There's one by Jesse Jenkins' group at Princeton, the Net Zero Americas project. There's one by Jim Williams and colleagues that was published in AGU Advances. There's one by Chris Clack and Vibrant Energy. And what they all tend to show is that, renewables play the bulk of the role in the next 2 decades at least. After 2040, some of the models have a lot more nuclear, depending on their assumptions around future costs. But for the next 2 decades, it's primarily a renewables game. But the fact that the US has so much natural gas infrastructure, in fact, we have too much gas infrastructure in some ways. Our typical gas plants today operate at less than 50% capacity.
Right.
The gas ends up being really effective at filling in the gaps between renewables, because gas plants, most of the cost of operating a gas plant is burning the natural gas. A modern natural gas combined cycle turbine that produces a gigawatt of power, so the equivalent of a medium-sized nuclear reactor, employs about 23 people. Compared to 140 people or so at a equivalently sized coal plant, and about 700 people at a similarly sized nuclear plant. And so if you have that coal plant or nuclear plant shut down for all but an hour of the day, you're spending a lot of money paying people to do nothing. There's a lot of fixed costs around maintenance and things, whereas gas turbines are dirt simple from a technology perspective, mostly automated, and have relatively little sort of non-variable operational costs. And so being able to dial down that gas plant and leave it idle for 60, 70, 80, 90% of the time, and only run it when the price of electricity is really high because the wind isn't blowing and the sun isn't shining, and you've had multiple days in a row of high demands where all your batteries are tapped out, that actually fits really well. And so what a lot of these energy system models end up showing is the amount of gas capacity in the US, the actual amount of gas plants, doesn't change much at all between today and 2050. But the capacity factor of those gas plants goes down from about 50% today to about 5% by 2050. And by 2050, you're burning a blend of like 50% hydrogen, 50% natural gas in those plants.
This is we did an episode on Pro Wind Gas Vegan Plus, which is a Greenpeace energy division in Germany, which is mixing electrolyzed hydrogen at a concentration of less than 1% into Russian gas and greenwashing it that way. It's interesting.
Well, yeah. I think less than 1% isn't much, but eventually we can get up to somewhere around 50%.
They're adding in. I think they've updated this year. Maybe under pressure from this podcast, probably not. But they've added in. I think 8% biogas now, but from vegan sources for the vegan blend, which is for the ascertaining customer as an extra, European scent or something. But
one thing that's consistent across pretty much all the energy system models, be they these new state-of-the-art grid integration models that are coming out in the US, or the like big coarse IPCC models, is you have sort of a loading order of fossil fuels in decarbonization scenarios. Coal falls off a cliff if we have any hope of limiting warming to below 2 degrees. Right. Oil peaks in the next decade or so and starts declining as more and more people buy electric vehicles. And then gas is the last to decline. It might even increase globally through 2030, even into the 2040s, and then falls pretty quickly. Sooner than that in 1.5 degree scenarios, a little later than that in the under 2 degree scenarios. But you essentially get rid of your coal first, your oil next, and your gas last. Right. That doesn't mean that you don't do anything about gas in the meantime, right? You're still reducing the amount of gas you're using by building more fuel-saving resources, be them renewables or small modular reactors or other things that can sort of load follow and fill in the gaps effectively. And in fact, one of the better arguments for clean firm generation, like nuclear, like geothermal, is it's really hard to get rid of gas in the system with just wind and solar and batteries. Well, that's an interesting anecdote. Things like what happened in Texas, right, where you have a long period of extreme demand and low renewable generation. Even if you had all the batteries in the world, they're going to run out after a few days, and you're going to be in trouble if you don't have some sort of on-demand generation that can fill in the gaps.
I mean, certainly, yeah, the fuel saving argument I think is quite strong. But I mean, if you look at Germany with the Energiewende, they've still got that 90 gigawatts worth of firm capacity on the grid. They've just built 110 gigawatts of wind and solar capacity. It doesn't seem like it's a way to fully retire a fossil fleet. It's got to be there in the background, particularly if, like Germany, you care about your industrial sector still being viable and not facing blackouts. And I think there was a $200 billion loss after the Texas blackouts with a number of industries.
I mean, it's tough. Like you can create a model where you can solve it with just renewables. Right. It just ends up being a lot more expensive. And in fact, one of the things that a lot of these models tend to find is that once you get from like 80 to 90% of renewables to 100% renewables, your costs roughly double.
Yeah.
So it's really an 80-20 problem, right? You can get 80% of the way there with renewables without much, if any, net additional costs. It's that last bit that becomes really hard, even assuming, a super grid and dramatic declines in short-term battery storage and all these other complementary technologies that can help renewables. Even with all those, you still have this last 10% problem where clean firm generation, makes things a lot cheaper.
I have this thesis I need to test a bit further, but I think absent the fracking revolution, we were kind of heading into a bit of a nuclear renaissance. Obviously, Fukushima had a massive impact on that, but I think without, like, in a world where we are actually peaking with fossil and we were not going to have a dispatchable source to firm renewables, I think you would be heading in a much stronger direction towards nuclear. Because again, if you didn't have this burst of gas over the next 80 years from fracking, wind and solar would really not be viable, particularly as we wait for the miraculous battery tech that's supposed to sort of salvage the intermittency and release us from gas eventually. But to be tested.
When we talk about battery tech, we should really differentiate, right? Like daily storage is becoming more and more mature, and that plays a huge role, right, in getting solar power from the daytime to the nighttime, for example. But the real challenges are around seasonal storage.
Or multi-day.
Here in California, our solar panels produce half as much electricity in the winter as in the summer. And so, you can either build 100% more solar than you need and throw half of it out in half of the year, or, figure out some other clean firm generation to fill in those gaps. But yeah, I think there is a case to be made there. At the same time, like, I don't want to throw all of the challenges of the nuclear industry on gas. Gas has certainly been the biggest driver of retirements of existing nuclear plants in the US, which has been a real tragedy. But I think the challenge around building new nuclear plants, at least in the West, has been more around construction costs than gas competition per se, though gas hasn't helped. Like, I'm not sure a world where we didn't have the fracking revolution, we would have really managed to solve the construction cost overrun challenges of things like the Vogtle plant. And, places like China, South Korea, Japan, where there isn't cheap, plentiful natural gas, haven't had a nuclear renaissance during that period.
Well, I mean, China's kicking ass now for sure.
China's kicking ass now, of course. Yeah. And they're going to be, to the extent to which I think there is going to be a big renaissance in conventional nuclear reactors in the next 2 decades, it's going to be in China. Just because they're good at building big things quickly.
I've got an interesting show coming up looking at nuclear in Africa, and my guest is positing that it's more likely to be countries like China with the experience of exporting the 300 megawatt reactor to Pakistan, like on budget and on time, that will be filling that gap, with the kind of state-backed capacity than, a lot of these Western startups that just don't have the state backing to offer the training and, full spectrum of services to a country, such as like NuScale, for instance, that has an interesting reactor design, but it's going to be an interesting show. I think there's definitely a case to be made for that. Like, particularly for countries that want big reactors, China is going to play an increasing role there in exporting that technology globally if they succeed in their current build out. Yeah, absolutely. Zeke, this has been a really fascinating, far-ranging conversation. You answered a lot of my questions for sure. I mean, there's so much here to take away from. I was going to end with something corny about trying to imagine, our kids in their 80s sitting on the porch together and kind of what they see. But I think this is just illustrative of there's so much uncertainty in these models. There's certainly the potential for some serious badness. My former guest Mark Lynas was saying with these non-trivial chances of heading into 4, 5, 6 degree territories, the degree to which you face a risk determines how much you're willing to spend on the insurance policy, right? the urgency seems there for me. I think my position kind of entering and leaving this conversation is pretty similar in terms of feeling highly motivated to make that change. And again, I mean, the idea behind the podcast, and I think that draws out of the eco-modernist tradition, is that hopefully we can have our cake and eat it too, and see human flourishing without severe climate or environmental impacts if we make the right technological choices. And the podcast posits that we need the right politics to enable those choices. I didn't mean to end on such a little spiel.
No worries. I mean, I just give a final note that, I am increasingly optimistic. If we look at all of the pledges that countries have made today, and again, pledging to do something 30, 40 years from now should be taken with a boulder of salt until it's reflected in near-term policies.
Right.
But if we add up all the pledges that countries have made, it ends up with us at a best estimate of 2 degrees warming by 2100. And that's a very different world than we had only a few years ago, both in terms of the magnitude of near-term pledges, but certainly in the magnitude of longer-term pledges. And so I think, we're moving in the right direction. Every year, the new reports come out and they show lower and lower future emissions trajectory on the sort of current policy or stated policy scenarios. And, we're just not doing it fast enough to get to where we want to go. So I think we're starting to make the worst case outcomes a lot less likely, but we still have a long way to go to get to the best case outcomes.
Yeah, I mean, I think talk is pretty cheap. I mean, Biden's talking about getting to zero carbon electricity by 2035, while retiring probably 5 gigawatts of nuclear in the next year and a half, maybe. I mean, I share with you, I think I've become a bit more of an optimistic person, particularly since becoming more solutions focused than problems focused. And I mean, I, for one, seriously was considering not having kids, and God, I'm ever glad I did. It's, fatherhood's an absolutely amazing experience. But yeah, I mean, very complex thing to look at. I think you were mentioning Václav Smil earlier in our talk, and I was talking with Mark P. Mills a while ago, and he was saying, listen, like, we've been through a number of energy transitions, but we still burn wood. Like, none of these fuels ever truly goes away. And I do take with a boulder of salt a lot of these stated commitments, like Biden's, or even the Tsinghua plan coming out of China, which, that to me, I was like, wow, this is really optimistic. China's going to be, the world's top emitter, the largest economy. They'll signal to the rest of the world sort of what to do next. This is big and bold and beautiful, but whether it's kind of geopolitics and trying to sort of seize that moral leadership on the world stage by making these pledges, talk is cheap, but I guess we'll see. We'll see.
I mean, for me, we were muddling toward a 3-degree world. We have commitments, long-term commitments to get to a 2-degree world. If we have the difference and end up at 2.5 degrees, that's not a world I want to live in, but it's certainly a lot better than one we could end up with.
Fair. All right, Zeke, thanks for taking the time, man. You have a pretty stellar depth and breadth of knowledge on this topic. It's been a pleasure having you on to demystify a little bit for us.
Yep, it's been great.
All right. All the best, man.
Take care.
If you enjoyed the podcast, please make sure to subscribe, like, and review us on your podcast platform of choice. Until next time, guys.